All right, so as you guys are finishing up your answers for numbers 5 and 6, number 5 said to show work. What would showing work look like here? 0 times what? 0.15 plus 1 times 0.42 plus 2 times 0.32 plus 3 times 0.08 plus 4 times 0.02 plus 5 times 0.01. So that's what showing work would look like. And then you can calculate each of these and add them together, or you can use the lists on the calculator to find the expected value. What do you get for this one? About 1.43, yes. And we're going to stick units with that because that 1.43 is telling us the average number of Home Alone movies watched. So 1.43 movies. And my interpretation of that, the mean is the same as the average. So my interpretation would start with the average. The average what? The average number of Home Alone movies watched. I didn't have enough room to fit the words Home Alone in there, so I just put movies. If I'd had a little bit more space, I would have done that. The average number of movies close. Remember, they said that this was taken from a very large sample of high school students. So if I were to repeatedly pick out a random student from the people that were included in this sample, and I did it over and over and over and over and over and over and over, then in the long run, after choosing many, 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 many students, the average number of movies watched would be 1.43 movies. And what did we get for the standard deviation? .97, yes. If you just wrote down 2 decimal places, that's fine. More decimal places is always fine. Personal preference, please refrain from giving me 8 or 9 decimal places. It's a lot to look at. It's a lot to write down. It's not wrong if you do, but you are never going to need 8 or 9 decimal places. If you like giving a lot of decimal places, 3 or 4 is usually going to be sufficient. 5, if it's like you're going to turn it into a percent, that's about as far out as I would ever go, would be 5 decimal places. But usually 3 or 4 is fine. What does that 0.97 mean? The amount of movies watched or the number of movies watched, same thing. What'd you say? I still can't hear you. Something about the mean, yes. Typically varies. The number of Home Alone movies watched by a student typically varies by 0.97 from the mean of 1.43 movies. Typically varies by 0.97 movies from the mean of 1.43 movies. While you guys are finishing up the notes on that page, I'm going to bring around an index card for you to choose from that we're going to use on the next page, on page 5. You're only going to use this index card for a moment while we do the first couple questions, and then I will be recollecting these because we won't need them for the remainder of the activity for today. I'm going to have 2 hands going here to get them spread out. All right, choose one card. card. Choose a card. Thank you. All right. So if we turn over to page 5, suppose you got a new job, and each day your boss draws a slip of paper from a bag to determine your wage for the day. That's what I just went around and simulated with you guys. Instead of me drawing the slip from the bag, I let you draw the slip, draw the card. Let the random variable X equal daily wage, dollars per hour. This is really important here. Taking the time to define the variable. This is essential. Always define your variable. All right, and then on that line, when you turn your card over and look at it, I would like for you to write what your wage for the day is. Write down whatever you got on your card. There were 6 different numbers on the cards. There was 1, 5, 7, 10, 15, and 25. And we had a lot of leftover cards because we have a lot of people out today. So it's possible that nobody got one of the ones on there. Just depends on how it all played out. So I'm going to go around the room. We're going to write down the probabilities. So first I need to get a tally count of who got which numbers. And then we will find our probability. London, I'm going to start with you. What did you get?
15.
You got 15. Nice. Taylor? 5. Palafox? 7. 10. Woo, 25. Ule? 10. Ade? 15. Alex? 1. Jayla? 7. Jack? 25. Javen? 5. Sage? 7. Juwan? 5. Edgar? 10. Tori? 7. And Jaylicia? 10. All right. So how many people are in the room today that drew a card? $16. So let's write down our probabilities. What's the probability that somebody made $1 per hour for the day? 1 out of 16. Go ahead and fill in the rest of the probabilities across this table. All right. What I have up there should be what you have. Yes? All right. Let's go look at question number 2. Is X a discrete random variable? Is this random variable X a discrete random variable? Yes. How do you know? Yes, it takes a countable number of values. They're only whole numbers, but it doesn't go on forever. It has a definite beginning and a definite end to this group of numbers. And there are gaps in between the numbers. In some cases, large gaps, like in between 15 and 25, we have a gap of 10, but that's okay. So we have a countable number of options with gaps in between. What is the probability from this class that a student makes $17 per hour or more? Two out of, what'd you say? 2 out of 16. So let's talk about our probability notation here. Big capital P for probability. And then inside parentheses, we put the event. We never put our fractions or our probabilities inside the parentheses. Here's where we put the event that we're interested in. What was the event again? 17 or more. That a student makes $17 or more per hour, right? What did we have to represent how much a student makes? X. So we want the probability that X is greater than or equal to 17. And you said that probability was what? 2 out of 16. Do you think this would be a very good way to determine wages for the day? Probably not. So let's look at a second option. Option number 2, your boss decides she could also assign wages so that employees would get any amount, even crazy decimals, between $10 and $20, and all the amounts are equally likely. Let Y, new variable, let Y equal the daily wage for this scenario. Oops, when did this come? Is Y a discrete random variable? No. I like your answer of no. Tell me why you said no. What'd you say? They all come right after each other. Using this model, would it be possible for somebody to make $12.75 per hour? Could they make 12.752391 per hour according to this model? Absolutely. We can have all these crazy decimals in here. So is it a countable number of values? Are there gaps in between the numbers? No. Y has infinite possible values with no gaps. And so we would call this, instead of a discrete random variable, we call this a continuous random variable. Y is a continuous random variable. What is the probability that a student makes $17 per hour or more? And this is where my graph comes in up here. Do you guys remember looking at these uniform density curves? The most somebody could make here is how much? $20. So we've got a cutoff here at $20. Can't go any bigger than that. What would this area be? It's always going to be the same when we're looking under a density curve. 1. So the area underneath the whole thing is 1. I need to figure out how high up on the y-axis this is going. What shape have we created here? A rectangle. How do you find the area for a rectangle? Length times width. Area equals length times width. And we already know what the area is going to come out to be, right? The area comes out to be 1. Do we know the length of this? From what to what? It goes from what to what? From 10 to 20. How long is that? 10 times my width, or I could think of it as height since it's the y-axis. Doesn't make any difference whether I say length times width or length times height. So how high up on the y-axis is this bar? What would I need to do? Yep. Divide 1 by 10. We're going to divide both sides by 10. So it goes up 1/10. Or you could put 0.1. That would be the same thing, right? We want the probability that somebody makes $17 per hour or more. So here's 17. Which way should I shade it if I want 17 or more? Should shade it to the right. This is what we want the area of. And it's a rectangle, right? So again, we're going to do length times width. I know how high up it goes. We just calculated that because it's the same height all the way across. How wide is it? 3. So what is this area here? 0.3. So what would the probability be then if I asked you for a percent? 30%, yes. The probability that y is greater than or equal to 17 would be 3 times 1/10, or you could do 3 times 0.10, and we end up with a probability of 0.3 or 30%. Yes?
This is also just like 10 minus like 3 gives you like your 30%. Would that work for every case? Like, or, I mean 10 minus 7 would give you your 30%. Would that work for everything or only for this?
For this one, it's just kind of how the numbers are falling. What you would want to do is you always want to find the length and the width on a uniform density curve like this, on a uniform probability model. You always want to know, it's always going to have a starting and a stopping amount. So you can always figure out, like, how long is it? You use that then to figure out its height. It'll always be 1 over whatever the width is. And then to find the probability underneath the curve from between any two values, you're finding the area, so length times width, or base times height kind of thing, yes. But yeah, on this one, we just kind of ended up with a happenstance on that. Let's look at a third probability model. Option number 3. Wages are assigned randomly from a normal distribution. Do you guys remember talking about normal distributions in the past? They're back. Wages are assigned randomly from a normal distribution with a mean of 15 and a standard deviation of 3. Let Z equal the daily wage for this scenario. Is Z a discrete random variable? What do we need for it to be a discrete random variable? Needs to be gaps in between, and it has to be a countable number of options. Well, looking at this, I see that they have labeled the y-axis, but are these the only possible values for wages? No. So do we have gaps in between? No. See how it continues all underneath this. This would not be considered a discrete random variable. There's an infinite number of possibilities. Between 6 and 9, we could do 6.1, 6.125, 6.27398. We could have 7.514. all the decimals in between these numbers, not just the whole numbers. So we don't have gaps in between. While there are gaps on the x-axis, there aren't gaps in between the numbers. And we don't have a countable amount. So z has infinite possible values with no gaps. This would be another example of a continuous random variable. Most of the time, when we have a discrete random variable, we will either be given a table for that discrete random variable, or we will be given enough information that we could make a table for that discrete random variable. When we describe things as uniformly distributed, everything is equally likely, or normally distributed, we're looking at these continuous random variables. So here's my normal curve. What's right down the center of that normal curve? What is this? That's the mean. So that's mu. We always want to label that on our normal curves. There's something else that my normal curves always have to have. I need an n to tell me that it's a normal curve. Next semester, we'll learn about other curves that look very similar to this one, and that's why it's so important that we label this one with an n. The other ones are different, but it's hard to just visually tell the difference between them if you're looking at the two different curves. So we're going to label that it's a normal curve, and then we have parentheses. Inside the parentheses, we need our mean, and we need our standard deviation. What was the mean here? 15. And what was the standard deviation? 3. You put it inside the parentheses, separated by a comma, and you do need to label each of those values. The reason that we have to label those is different textbooks, different people approach statistics. Sometimes they'll flip it around the other way. Sometimes they'll have the variance instead of the standard deviation. So we are labeling exactly what we have here. It is standard in AP statistics that it's the mean first and then the standard deviation, but the AP reader is not going to know exactly which textbook you used or if I stressed that particular piece or maybe we did it differently. So that's why we have to go through and label those parts. What is the probability that a student makes $17 per hour or more? First, I want to shade the region I'm looking for. Sorry, Sage, do you have a question?
When we label it, could we also just put like mu equals 15, sigma?
Like inside the parentheses? Yes, you can absolutely do that. Yes. Honestly, the only reason I didn't here and why I usually don't is because I usually run out of room horizontally, and I tend to have more room vertically. But if you have room to write it out horizontally, you want to write mu equals 15, comma, sigma equals 3. That is perfectly appropriate there. Yes. All right, finding the probability that a student makes $17 per hour or more. I need probability notation for this. And I need shading on my graph showing what I'm finding the probability of, what I'm finding the area of. Remember, the area under these density curves is always 1. So the area that I find is the same thing as the probability that I'm finding. So I need to go and find 17 on this graph, which would be about here. Since they don't already have it labeled on the x-axis, we need to label that, 17. And then which way should I shade that? To the right. I want 17 or more. And then my probability notation needs to mirror what I've just shown on that picture. Probability notation always starts with what? Big capital P. And then in parentheses, I'm going to have the boundaries of what I have shaded. What's the farthest to the left that we have shaded? 17. And then from there, do we have a stopping place on the right? Nope, it goes to the edge of my graph. If my graph was made wider, it would continue going on. So probability that z, my random variable, is greater than 17. This is not a uniform density curve, so I can't do base times height or length times width here. Do you guys remember how we calculate the area for a normal distribution? Normal CDF, yes. We're going to do normal CDF on the calculator. And there are some values that we're going to have to enter into the calculator. What's the first value that we need to enter? Lower boundary. What's our lower boundary, the farthest to the left? 17. And I'll show you how to put it in the calculator in just a minute. For right now, I just want to kind of get it written down on our page in case you don't remember where the buttons are. If you want to do them both at the same time and you remember where the buttons are, go for it. My lower boundary is 17. We have to label that as lower boundary. And stage, this is another one where you could have LB equals. What's our upper boundary? What's the farthest to the right that we have this shaded? What'd you say? Infinity. It goes on forever. I'm not going to put an infinity in here, though, because the calculator needs to actually take a number. So I'm going to pick a really big number, something like, I don't know, do you think 1 million would definitely catch everything? So after I put my lower bound and my upper bound in there, I need 2 more numbers. What do you think those 2 numbers are? Mean and standard deviation, the same thing that we put in the parentheses up there. All right. I'll come right back to this screen, but I'm going to flip over to my calculator for a minute so that we can practice putting this into the calculator. All right. So to get to the normal distribution, we go second and the vars key right here. Oops, second and vars. If you look right above the key that says vars, in little tiny letters, the same color as your second key, it says DISTR for distribution. This is where we go to find these different distributions. We want normal CDF, which is option number 2. This is where we put in our lower and upper boundaries. If you're using the app on the phone, you just have to enter the numbers with commas in between. We said our lower boundary was 17. Our upper boundary, we went with something stupidly enormous. So we had 1 million. Then our mean of 15 and our standard deviation of 3. And then you want to paste that in. Hit enter. What'd you guys get for the probability? Yes. 0.2525 if I round it to 4 decimal places, right? About 0.2525. All right, let's go back and we're going to write that down on our page. All right. Let's flip it over and recap kind of our big ideas, our learning topics for today. Types of random variables. There are 2 types of random variables. Yesterday, our focus was on discrete random variables, and we practiced again today with discrete random variables, talking about the amount of money you make per hour if it's just drawn on a slip of paper. Discrete random variables, always a countable number of values, so it's never going to go on forever. It's always got a defined starting and stopping position. And there's gaps in between these values. They can all be whole numbers. We can have decimals. Like if I said you're going to make somewhere between $15 and $16 per hour. If I'm talking actual money, I could only go out as far as pennies, right? So those would be considered discrete. Continuous, we have an infinite number of values with no gaps in between. And two examples of that we did today are uniform and normal. For our probabilities, we want to find the area under the curve. With uniform, it's always going to be base times height because we have a rectangular shape. The height will always be 1 over however wide this is. And for my normal, oftentimes we want to calculate a z-score. I didn't do that today for time. Do you guys remember talking about calculating z-scores? We do our x value minus the mean divided by the standard deviation. Do you guys remember what a z-score is showing us? The z-score tells us how many standard deviations away from the mean we are. Do you remember how many standard deviations on either side typically fit under the normal curve? Yeah, it's a little bit more than 3, but it's right around 3. We have 3 standard deviations that takes us out to just about the boundaries. The z-score tells us how many standard deviations away from that center we are. Positive z-scores would be that far to the right. Negative z-scores would be that far to the left. If you calculate your z-score, you can use table A from the formula sheet to find the area, or you can use your graphing calculator like we did today. I want to give you guys about 5 minutes to do the check your understanding. There is one change that I need you to make, and it's on part C. On part C, do you see how in the probability notation it goes from 90 on the low end to 1,200 on the high end? That had one too many zeros in it. Please change that to 120. Should be 120, not 1,200, right? Please make sure you draw pictures just like we did. You're going to have to draw your own normal curve there for both part B and part C. Flip it over on the front if you need a model. We're going to take about 5 minutes to do that, and then we'll come back together. While you guys are working on that, I'm going to come around and pick up the index cards. Is this random variable m discrete or continuous? It is continuous. How do you know? Yes. There are an infinite number of possible times for playing Minecraft with no gaps in between. Time is almost always a continuous random variable. All right, so let's look at part B. Your picture that you drew, if you didn't draw one, you need to get one on your page, should look something like this. You need to have your curve. Straight down the center of the curve is where you want your mean. You need to have n showing me that it's a normal distribution with the mean and the standard deviation inside parentheses and labeled. You need to have the boundary marked on the graph. We wanted to find the probability that m is less than or equal to 90, so I have that boundary of 90 on there, and then I have it shaded to the left for less than. What does the probability notation look like for this? They gave it to you. What does the probability notation look like? Big P, m less than or equal to 90. And then how do we actually calculate this probability? Normal CDF, negative a million. That would definitely be far enough out to the left that I'm guaranteed to grab everything over there. Negative a million up to, what would my upper bound be? 90. And then what do we need? Mean and standard deviation, so 150 and 42.7. Make sure you are labeling those. Different calculators have you put things in a different order. One of the things that they are always looking for on questions like this on the AP exam is, do you know what these different values are, what they mean? Usually there are pieces on the rubric for, did you correctly identify the mean? Did you correctly identify the standard deviation? Did you correctly identify the boundaries? If you write out that calculator notation and you label each of those pieces, you hit all of those ideas. If you write out the calculator notation without the pieces being labeled, you do not get those points. You do not get credit for that section on the rubric because you're not demonstrating that you know what these different pieces are. Popping that in your calculator, you get approximately what? 0.07999. If you rounded that to 0.08, I would accept that because it's like 0.99989 something. Now, what does that mean? What did we just find with that 0.07999? This is telling me part of my interpretation. What's that big capital B stand for? The probability. Yes, sir. Yes. The probability of selecting a Minecraft player, not just any Minecraft player, but this is the probability that I randomly select one of the people from this sample, the probability that they play Minecraft for less than 90 minutes a day. So there's about a 0.07999 probability, or the probability of choosing a randomly selected Minecraft player who plays less than 90 minutes per day is 0.0799999. There are ways that you don't have to write the sentence in that exact same order, but you have to talk about the fact that it's a probability. You have to give the probability. You have to talk about what that boundary means, that 90 minutes or less. You want to put that back in context. And you want to talk about random selection of whatever group you're looking at. So those are the big ideas that you need to have in your explanation. All right, let's look at number 3. Your picture should look kind of the same. What pieces stay the same? The mean stays the same. The 90 stays the same. What else stays the same? The standard deviation stays the same. But this time, we are shading in between 90 and 120. Still need to have your big capital M showing me that this is a normal curve. Having that big capital M, N, is also how you protect yourself if your normal curves don't look very normal curve-ish. And I understand, not everybody's an artist. I am certainly not. I trace mine because I'm not good at normal curves. But if you draw something that somewhat looks like a normal curve and then you have that big capital N, the reader is going to know what it is that you attempted to draw. All right, so what are we putting in the calculator? Normal CDF, lower bound of 90, upper bound of 120, mean 150, standard deviation 42.7. Make sure all of those different pieces are labeled. And what did you get? 0.1611. I got 1617. Depending on whether you use table A or technology, there's going to be a little bit of wiggle room. If your numbers match mine out to 3 decimal places, you should be okay. So as long as you match out to 3 decimal places, you should be fine.
My calculator said 0.16117.
That might be me misreading it too. I'll need to pop it into my calculator and see if I did it wrong, which is very possible. And then what is this the probability of? What did we just calculate?
Probability of choosing a Minecraft player who plays at least 90 hours to 120 minutes per day is about 0.167.
Yes. And you're right. It was 117, so I should change that to 1612 if I'm going to round it out to 4 decimal places like I did. So let me fix that there. So there is approximately a 0.1612 probability of choosing a Minecraft player who plays between 90 and 120 minutes per day. Absolutely beautiful. First homework assignment is due tomorrow. If you have not yet done the reading, pages 389 to 402, the reading will help you with the homework, as will the notes that we've done over the last 2 days. So I would have my notes packet handy, and I would have my book handy. If you guys are interested in which AP Daily videos would be of assistance, please let me know. I'm happy to let you know which AP Daily videos you would want to get in and watch. Even though I haven't gone in and assigned them, you still have access to them if you are struggling with this.